Today we're doing tangents and circumscribed angles. Um, One thing to note here is the word tangent has a very different meaning here than it did when we were dealing with the right triangles and triangles. Instead of being a tangent function like sine, cosine, tangent, here tangent has a specific definition. So be aware of that. Circumscribed, what does it mean to be circumscribed? Well, before, when we had a circle, we had an inscribed angle, right, that was in the circle. Now we're going to have a circumscribed angle that's going to be outside the circle. And the circle is going to fit perfectly inside that angle. So I'll show you what I mean here. First, we need to define tangent. Our new definition for tangent is any line that intersects a circle at exactly one point. So this line here intersects this circle at exactly this point, and we're going to call that point the point of tangency. It's pretty easy to imagine what would happen if we change this line a little bit, if we move it up or move it down. If we move it up, it wouldn't intersect the circle at all, right? And there's 0 points of tangency. If you'd move it through here, it'd be too low, and there'd be 2 points that would go through the circle. So that won't work very well. It would also won't work if you change the angle. And I'll explain what it would look like here. So if I was to just kind of rotate that line around point P and just change the angle, it would have now 2 points that it would intersect the circle at. So that doesn't work either. So a tangent, again, intersects the circle at only 1 point. And some of you may have already deduced this one, that tangent line. So here I'll draw the tangent line. This is the tangent line. When it does intersect, it's exactly perpendicular to the radius. There are an infinite number of radiuses coming out from this circle, right, all the way around. But if we draw a radius from the center to the point of tangency, right, that segment will be perpendicular to the tangent line. All right, so let's think about this one. If both lines in this figure are tangent to this circle, and AB is the diameter, right? It goes through the center, so AB is the diameter. What can we conclude about those tangent lines? I'll give you a second to pause. I'll pause it and you figure it out. Pause. Oh, stop it. Very weird. There we go. So they're parallel to each other, right? They're both perpendicular to the same line. So since they're perpendicular to the same line, they're parallel with each other. We can draw little parallel marks. Boop, boop. Boop, boop. Parallel. Cool. The opposite is also true of the tangent radius theorem, right? The converse. Remember here with the converse of a statement, the if portion, if a line is blah, 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 then it is blah, 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 blah. This is the exact same thing as the tangent radius theorem, but the red part and the blue part have been switched, right? The if and thens have been swapped around. So it's the same thing. Okay, skip that. If you were in class, I would have had you discover this empirically, but otherwise we'll just have to accept this and this circumscribed angle theorem. But first, we needed to define a circumscribed angle, and I kind of hinted at this before. When we have a circle, and this time the angle is going to be outside, so I'll draw my angle, my super straight line here. Wow, that was bad. Yeah, it is too bad. I can't accept that line. Yep, better. Okay. This angle is said to be circumscribed if the two rays are tangents of that circle. So there's this cool relationship that happens. We have a radius here. We'll put the center. I guess make it red. So I have the center of the circle here, and I can draw the radius to this point of tangency, and the radius to this point of tangency. This is 90 degrees, and this is 90 degrees. So in this four-sided figure, 1, 2, 3, 4, poorly drawn four-sided figure, the total of all of the angles is what? 360, right? So we're going to subtract 90 for that, subtract 90 for that. Therefore, the remaining two angles, this central angle here and this angle here, have to equal 180, because that's all that's left. So that's where the circumscribed angle theorem comes from. It says a circumscribed angle of a circle and its associated central angle, those are the two purple ones, are supplementary, right? That means that when you add them together, they equal 180 degrees. Okay, we'll see an example. We'll do a proof, but I just described it, basically. We know that this angle is 90, this angle is 90, therefore there's only 180 left between these two. So hooray for that. Is it possible for quadrilateral AXBC to be a parallelogram? So we're going back to this picture, AXBC. So is it possible to be a parallelogram? If so, what type of parallelogram must it be? If not, why not? I'll let you think about this for a minute. So pause. Ta-da. Yes, it is possible to be a parallelogram. Some people picked up that since it's a parallelogram, adjacent angles have to be supplementary, but those opposite angles have to be supplementary, and two of them are 90, so that means that they're all 90 degrees, and so it must be a rectangle. But furthermore, two of those sides have to be equal, right? AC has to be equal to BC because they're both radiuses, so therefore it has to be a square. A further note is if this one is equal to this one, and if this angle is equal to this angle, okay, we'll go back to the question here. It says Km and Kn are tangent to circle C. So this is tangent, this is a tangent. Explain how we can show that Km is congruent to Kn using congruent triangles. So we've just made these two conclusions, right? Well, I should make that a 90-degree mark. Moved it. Nope. Make that 90. Okay. So how do we know that Km is congruent to Kn? Well, guess what? We're going to split this into two triangles. And then whenever we make two triangles, we need to prove that they're congruent. So I know that KC is congruent to KC, MC is congruent to NC, and angle KMC is congruent to angle KNC. And those are both 90 degrees, right? So therefore, I can use what triangle congruence theorem? Think about that for a sec. Pause. Hypotenuse leg, very good. So we can use HL to show that the two triangles are congruent. And once we know the two triangles are congruent, we know that this segment is congruent to this segment because corresponding parts of congruent triangles are congruent, right? And that's basically what this thing says. Corresponding parts of congruent triangles are congruent, and we can prove them congruent here using hypotenuse leg. So, good job. That's pretty much it for this lesson. And the very last lesson, doing these basic circle things. We'll do more stuff using arcs and stuff like that later here. So anyway, have a good one.